last time we learned about multiplicative weight update, or I will just say weight update for short. Right? And today we will see its application. We can use it to solve like something called packing covering LP, which I will define later. But you see that the algorithm is going to be quite simple and nice. So, and it applies to much more than this. So, at least it's good to see how this thing works. Okay. So, the approach we're going to see today, is a kind of a general approach for approximately solving LP. And we're going to just go through one concrete example so that you kind of understand the techniques, which is how to solve maximum matching and vertex cover fractionally. But the idea will apply to like much more general class of problems, which is packing covering LP. Yeah, I will define it at the end. But like the first thing is to recall weight update. Yep. Okay, so in the setting of weight update, multiplicative weight update, there are n experts, right? And there are t days. Right? And the weight update algorithm with parameter epsilon works like this. It's just initialize the weight on all expert or on all I to be the same, just one. Right? And then for each day, we are given some gain vector. Last time I talked about loss vector, but just flip that, it's gain vector, like negative of that. So this is a gain vector, which is between -1 and 1. And we will just update the weight accordingly. That is, if the gain is a lot, gain is 1, then we increase the weight accordingly. If the gain is negative, then we decrease the weight. Okay. So that's what weight updates does. Okay. And then just from this is like what it does. Okay. But it does guarantee something. Okay. So what does it guarantee? So it cannot guarantee the relationship between the gain of our algorithm and the gain of the best expert. So what's the gain of the best expert? It's just like this would be the total gain of expert I overall time, overall day t, right? And you maximize overall I. So let G star is just, this is like, G star is the total gain of the best expert. Okay. I'm just recalling what's from last time. Okay. And then we also consider another one, which is like our gain. Okay. So if we say that WT is the total weight at day t, like just sum overall weights, right? Then our interpretation from last time is that on day t, we follow each expert with distribution like WT scaled down by like the total weight here. So our expected gain on day t is basically this thing, right? Like sum overall I WIT over WT times GT I. This is just the same thing as to write this inner product with WT inner product with GT. And so This is like our expected gain on day t. And so the total gain is just to sum over all days. Okay. So we look at these two things, the total gain of the best expert and our gain. Okay. And do you recall the relationship between these two? What do we know about these two quantities? Anyone? Yeah.
Our gain is going to be less than or equal to the total gain of the best expert?
Our gain is going to be less than this. Well, this is true, like in general, but like, so, okay. What did we show last time? We showed that like when we talk about loss, right? We said that our loss, like our loss is gonna be at most, like clearly at most the law, like at least the loss of the best expert. But it's also, we say that our loss is not too big compared to the best expert too. Like our loss is not too big. Some term here. So like that is like the algorithm should have no regret, right? Compare our loss to the loss of the best expert. It's not too big. Here, if we talk about gain, then what should we have? We should have that our gain is basically as good as the best expert, as big as the best expert, right? So we should like, what we should guarantee intuitively is like the gain should be like as big as something minus some, like something small here. This is what we have, right? And in like precisely, this is what we get. Our gain is as good as the best expert up to some term here, where this is like epsilon that you can set it to be small, and this is like some term like log n, which is tiny, right? And if the gain is between 0 and 1, is non-negative, then you also have a bit stronger guarantee here. Okay. So is the notation and is the interpretation of this clear with you? Clear out to you? Okay. All right. So basically what it says that like if some expert gain a lot, right, then MWU must gain a lot too. On the other hand, on the flip side, if somehow we know that the gain of MWU is tiny, then it means also that the gain of all expert must be tiny as well. And this is the perspective that we're gonna use today, actually. Yeah. So basically consider this scenario, right? So it's a scenario where you also kind of start with initial weight to be 1, initialize the weight to be 1. And there are t days. Like before, you're gonna set t to be something like this. Ignore this for now. And now, on each day, we are given a gain vector h. this gain vector is a bit different in the sense that now the gain is, okay, it's not negative, but it can be as big as rho. Rho can be more than 1. Okay. But we promise that this thing is small. How should you interpret this thing? What is this? Like, what's the interpretation of this? Yeah.
It's like the probability factor over all experts.
Right. This is like WT over the total weight is like the probability of like probability over expert. When you inner product with HT, what is this? Yeah.
This is saying that HT weighted by the probabilities is gonna, or like it's sort of like the expected value of HT is less than or equal to 1.
Yeah. Expected value of HT is less than 1. Meaning that if we follow the expert according to WT probability, our expected gain is less than 1. This is what it means here. So let's say I promise you that like I'm giving a gain vector such that I promise you that like our expected gain is small. Okay? This is what it means here. Okay, and then I update the weights. It's not quite epsilon here, but epsilon over rho, which kind of makes sense because of this factor rho here. If you scale it down by rho, then h over rho is kind of at most 1. But this is like something similar to before. Okay. And now we look at this one. If you take sum of HT over T, this is just the total gain vector of each expert. Like, it's just a vector that have like n-dimensional, and it's basically this encode the total gain of each expert, right? And so H bar is just this thing over T, which is like average gain, how much is expert gain per day on average. Okay. So now my claim is that the average gain of each expert I, H bar I, is going to be small too. Basically 1 over like 1 plus something small. So why does this make sense? Because it basically says that like if our expected gain per day is small, like our average gain per day is small, then the gain of every expert must be small too. Okay. So you don't need to see the proof of this right now, but at least it should make sense to you. That like if we do something similar to weight update, then it must be the case that once our like a gain of the weight up, once the expected gain of the weight update algorithm is small, it must be the case that the gain of every expert must be small too. Okay. So let's try to prove this now. Okay. Okay. So again, the interpretation of this is like here, yeah. The gain, like weight update has small gain per day. This is what it means here. Okay. But right now, like we cannot really apply our weight update theorem directly, just because the gain here is not between 0 and 1. It's like between 0 and rho, which is a bit bigger. So all we need to do clearly it's like try to scale things down and see what we get, right? Okay, so let's try to prove this thing, which is this. Okay. So yeah, naturally what I'm gonna do is just try to scale h down by row, and now we get like a let gt be like a ht over row. So now like gt is just between 0 1 now. Like this is like a gain vector like before, and you can see that the way that we update the weight here, like gt is h over row. So the way we update the weight is just that now like update the weight with a factor of 1 plus epsilon g, which is like before in the weight update. So this is exactly how weight update algorithm update the weight with respect to the gain vector g. So we get this thing just from our theorem of the weight update. And now what we need to do is just try to kind of analyze like what does this, how this implies that the average gain of each expert must be small. Well, what do we do? Like I'm just gonna multiply all this, the whole equation by rho over t. So multiplying by rho makes sense because like we wanna multiplying by rho makes sense because we wanna argue about h, and h is like a rho times g, right? And dividing by t makes sense because we want to talk about average gain per day, not total gain. Okay. So let's analyze this and this when you multiply rho by t. So this is, I just multiply rho by t to this thing. And just from the definition, this is like a total gain of the weight update algorithm. Multiplying by rho to g here, you get h. And average, like dividing by t here, is just like dividing this by t. Like so, basically each of this term is at most 1 from our promise, right? Like from our promise here, and so this is just the average of 1. So this is at most 1. Okay. What about this one? When you multiply g star by rho over t, this is just from the definition of g star. Now, like I multiply rho to g, we get h, and then like so we can say like this is equals to 1 over t max max I 1 over t sum h I t. Okay, and this is then, this is just, yeah, this is just like the total gain of expert I, and you average over all days. So this is h bar I. Okay. So basically, this term is at most 1. This is at most 1. And this term, this is at least hi bar, right? So what we get here is like 1, and this factor, this is hi bar, and this term become this because we multiply by rho over t. And once we like just by rearranging, because t is like t is set to be big enough so that this term, like t is set to be here, so that this term is just epsilon. Right? So I just rearrange and I get this one, which is at most 1 plus 3 epsilon. Okay. So there's nothing deep going on. We really just now can say that the expected gain, like the average gain of every expert must be small too. If first of all, the gain of weight update is small on each day, and we have enough number of days. Okay, just so that like we average, like we have enough day to average over. Okay. Okay. Everything's clear for now? Yeah? All right. Good. So keep this in mind, right? Yeah. If I can promise that the gain of weight update is small, then the gain of every expert must be small too. Okay. By the way, like here is an exercise for you. Oh. What if the gain can be negative? Then you can try to show this yourself. That if the gain now can be negative, then I will need like a number of days to be like proportion to rho square to guarantee that the gain of every expert is small. Okay. So we actually like, can exploit that, like the fact that the gain was non-negative, we don't need as many number of days as when it's negative. So, but we will not use this today, but it's useful for you to see this. Okay. So now, with that in mind, about like how weight update algorithm guarantee you, like we're gonna try to use it to solve LP approximately. Okay. We haven't seen so far how to we have seen how to solve LP in the online setting, but usually that gives some bad approximation. And we didn't learn any black box to solve LP exactly. What we see today is how to solve LP really like with good approximation, like a 1 plus epsilon approximation. Okay, so and for concreteness, let's look at the graph, at the some graph problem, where you have a graph G with n vertices and m edges, right? And now we can write the LP for maximum matching and vertex cover, which is dual to each other. This is the LP for maximum matching, right? The total, the total fractional value of the match edge cross so what does it say? For every node V, the total number of XE incident to this is going to be at most 1, and we want to get a maximum matching here, and this is LP for vertex cover. Okay. I think you have seen this several times, so okay. Now this is good for concreteness, but sometimes it's just nice to write it succinctly as well, right? So this thing can be written like this, where this is just a matrix A of this dimension V times E, where AVE is 1 if V is an endpoint of E. Yeah. And this is, once you define a matrix like this, I can just write this linear program to be here. Yeah. All right. And this linear program is just here, where this is A, X, so this is going to be A transpose Y. All right. So this is a linear program that we want to solve approximately. Okay. Not that I don't want to solve this problem integrally, right? I want to solve this linear program. So I would return some fractional solution. That's the goal for today. Okay, that's the goal. Let's try to compute like 1 plus epsilon approximate solution to both LP. Okay. And to solve this for both LP, you need like the following is going to be sufficient. That is, I'm going to solve like kind of decision version where I give a guess on optimal value. Let's say op is a guess. And then let's say epsilon is some accuracy parameter. So what we're going to do is just to return like either like a feasible fractional matching. That is like X is a feasible solution to P, right? Such that the size is like close to opt, 1 minus 4 epsilon opt, or return here like a feasible solution to dual. That is feasible fractional vertex cover Y such that the size is at most opt. So this one certify that opt is at least like the optimal value is at least this. This one certify that the optimal value is at most this, because this is like a feasible solution in the dual, right? Okay. So do you see that if I have, do you see why if I have this subroutine, then I can get like, I can indeed get the approximate solution to both LP. Do you see this? Say yes or no. No, okay. So basically like this thing, right? So you think like this, right? Let's say that this is optimal value of P, which is the same as optimal value of D, right? And I'm just gonna kind of guess for opt. If I'm kind of below here, then I will basically return X, which says that like opt is gonna be at least this one, suppose, yeah. And if I get here, if I guess opt to be here, then like clearly I'm gonna return something here, which certify that opt is at most something. So basically, like actually like if I guess opt here, I will return X such that the size, like return X such that the size here is at least like 1 epsilon opt. So like slightly below opt here. So this is a bit confusing. Opt here is like the guess, yeah, not the real optimal value. This is like the real optimal value. Okay. But you can see that with this subroutine, we can kind of binary search to find like to be close to this guy. And basically I can, at the end of the day, I can return some fractional vertex cover, which is close to this guy, and also fractional matching, which is close to this guy from below. So once we get 2 of them, which is close to the real optimal, they must be basically near optimal, both of them. Yeah.
Could you also put the epsilon on the vertex cover side if you want?
We can, yeah. This you can put 1 plus epsilon here too. You can still do this approximate binary search. Yeah. Okay. Make sense? Like, so it's really enough for us to just get to solve some kind of decision version like kind of either return the meshing or return vertex cover, and at the end we will get like like near optimal solution for both. Okay. So from now, our goal is to just solve this one, like given opt as a guess, return matching of size close to opt, or return vertex cover of size at most opt. Okay. So to do this, we're gonna look at an oracle problem. This is like a concept that is good, like that is important in this class. Okay. So the key idea is that we will not solve the LPP directly, but we will actually reduce the problem to a much easier oracle problem, okay, which I denote by oracle given some weights, W. Okay. So what is this oracle problem? Let's see. Okay. Let's say that I'm giving a weight, the weight on each vertex. Or you can think like, if this is a weight for each constraint to the constraint of the LP. Because the LP, like the fractional matching LP has the constraint for each node, right, for each vertex. So we get like, let's say W is like the weights that you put to each constraint. Now the oracle problem for W, for the problem for LPP is to find X such that first of all the size of X is at least opt. And next we want X to satisfy this. What does this mean? This is like you multiply W V to each constraint V and then sum them up. Right? What is this? It's like you used to have like for node V1 you need that like every edge that contains V1 is at most something. For V2 every edge containing V2 at most 1. And what I do is like I multiply WV1 to here, multiply WV2 to here, and then sum them up. Sum this thing up. Like WV1 to both sides, actually. Like WV2 to both sides, and then sum them up. This is just what it means here, right? So you see that what this is just kind of, you used to have many constraints that need to be satisfied like simultaneously. Now you just basically collapse them, like kind of average them into one constraint. Yeah.
Is there a difference in the type of T that you're using for the transpose of the notation?
Oh, sorry. Yeah, this is like T and T. Yeah,
Okay, same thing.
The same thing. Yeah.
Sorry, what you were describing there, was that the right side of the equation or the left side of the equation?
It's both sides.
Okay. So the summation is the W transpose AX, and then the less than or equal to 1 is like the W transpose 1Y.
Yeah, like so basically maybe I should write like I multiply W into both sides and then sum this thing up, sum every equation into one. So the right hand side is going to be just exactly this one, the sum of W. The left hand side is just going to be like just one constraint on x, like kind of linear. It's gonna be linear form of x, just single one. Okay. All right. So, is this clear? Okay. So yeah. So the goal is to find x such that it satisfies this, or report that is not feasible. Like that is said that there is no such x. Okay. So you see that like this Oracle problem is like an average. It's just average the constraint of all the from the LP into just one. Except that like this used to be the objective. I just now say that the objective is at least up. But all other constraint is just now collapsed to one. So it should be much easier to solve. Okay. And yeah, the true observation is this. We're gonna prove this formally. Basically, if the optimal value is at least opt, indeed, like our guess is kind of correct, like the optimal value is at least opt, then the oracle must be feasible. I show this soon. And also, if the oracle is infeasible, if you cannot find such x, then we can get a certificate showing that optimal value is at most opt. Which is just to say that what is the certificate? It's just a solution in the dual. If you get a dual solution with value at most opt, that's a certificate that upper bound opt. Okay, so let's try to prove this formally. So what I mean here is like, if there is a fractional matching of size at least opt, then for any weight, actually, for any weight at all, this oracle must be feasible. And that is kind of clear almost from the definition. If you understand that oracle problem is just the kind of easier version of the original problem. So why is that? Like, so let's say that x is a feasible solution, right? If x is like a fractional matching here, I claim that x star, this x star, I claim that this same x star is a feasible solution to oracle. Why? Because first, like here the size of x star is at least opt, so the first constraint here is satisfied. And yeah, like ax star is at most 1 for all vertices. This is true for every constraint. So if you just average all the kind of get a convex combination of the constraint, just multiply it and collapse to 1, x star would satisfy that too. There's kind of nothing to do. Okay. So this would be true for every weight. So yeah. So if the x is a feasible solution with at least with of size at least opt, then the oracle is feasible. Okay. And now let's try to prove 2. Okay. That is, suppose that the oracle is not feasible. Then let's say that W is the weight, the total weight. Then claim that I can just construct Y like this, just scale up W like a bit. And then I claim that Y is a fractional vertex cover of value of size opt. Okay, this is not supposed to be too clear. So but at least I want you to understand the statement. If it's not feasible, if the oracle is not feasible, then we can find a certificate saying that the optimal value of the original LP must be at most opt. Okay, that certificate is just a solution in the dual. Okay, so why? So now I need to show you that Y here is a fractional vertex cover. Okay, so so first let's prove that clearly first the size of Y here is opt. Why is that? Because the size of Y is opt times W over capital W. But this is 1, right? Because W here is a distribution, right? I mean, maybe I just do it like this. This is just over W, and this is W. What is this? This is sum over all W. So this is just opt over W times W. This is opt. Okay. So the size of Y here is opt. Now I just need to show you that Y is a valid fractional vertex cover. What does it mean? It means that YU plus YV is at least 1 for each edge. Okay. So suppose that this is not the case. Suppose for contradiction that actually there is some edge E prime such that YU prime plus YV prime is less than 1. This just means that just because Y is just a scaling of W like this, I just scale things, and then it means that the weight of U prime plus the weight of V prime is at most this. It's less than this. Okay. But now I'm gonna show a contradiction. That is, if the X is such a weight E prime, okay, such that the total weight is small, then what if I construct X like this? I construct X to be such that I put the value up on E prime and everything else is 0. This is my X. Okay. So we get that actually so what is the size of X? The size of X is just opt, right? Because it's just sum over all value of X is opt here. But I claim that this thing is less than W. It's less than basically 1 W1, which is, this is nothing but the capital W. So why is that? Well, this is WAX is just to sum over all constraint. AX is this is the constraint of V multiplied by W sum over all nodes. This is WAX, right? But we our X here, it has a value opt on only E prime. Everything else is 0. So this is just gonna simplify to to only like we're gonna get x of e prime on one endpoint, which is u prime, and x of e prime on another endpoint, which is v prime. So this just simplify to this one. Okay. But this is x of e prime. X of e prime is opt. And the sum of this thing is w over opt. So this is less than w. It's like strictly less than w. Okay. So it means that our x, this x, is a feasible, like show that like Oracle is actually feasible. Okay, questions. It seems I'm not sure you follow. Start with the statement. Is the statement clear?
Yeah.
Okay. And there are two things we need to show. That the size of y is opt and y is a vertex cover. Are we clear that the size of y is opt?
Mm-hmm.
Question? This is good. Okay. Now I need to show that y is a vertex cover. That is, like yu plus yv is at least 1 for all edges. That's the goal. So let's suppose not. Suppose not. That's not the case, and we're gonna show contradiction.
Yeah.
That is, if actually y is not a vertex cover, I actually gonna say that the oracle is visible. So that's give a contradiction.
I see.
Okay. So suppose that y is not a vertex cover, so there is some edge e prime such that this is like less than 1. Okay. So now what I'm going to do is just look at this edge e prime. Now I'm going to construct x that shows that the oracle is feasible, and that would give contradiction. Yeah.
And so X is a fractional matching?
X is not even fractional matching. X is just some, like X is not a fractional matching. It's a point that shows that oracle is feasible. Why X is not feasible? It's not a matching because I define X to be this thing. It's all 0 except that this is opt at e prime. This is more than 1. It's not. It's like this is not.
Yeah.
It's not matching.
Yeah.
But it's something that I claim that it's gonna show that oracle is feasible. Okay. So now I'm gonna show that like this X will show that oracle is feasible. Are we clear on the plan right now?
Yeah. Yeah.
Okay. So first of all, like there are two things to show that like the oracle is feasible. First, I need to show that the size, like the sum of x e is at least opt. This is just like this x. The second thing is just that is at most this thing. There are just two constraints in Oracle. We just need to show that x satisfies both, right? And the first one is clear from the how we define x. Just because the sum of this thing is at least opt. Okay, so let's show this thing. That's the last thing. Okay. What is this? Now just need to like kind of like unfold the equation here, right? This is like our interpretation. Remember, like this is the constraint on our matching LP, and we like basically multiply by W on every constraint and then sum them up. This is what it means here. So this is what I just write here. This is the left-hand side of the constraint, multiply by W, and then sum over all constraint V. Okay. Now I claim that this thing is gonna be at most W. Why is that? Well, like you can see that like basically most of the entry of X are 0. Right? Basically every entry of X is 0 except at E prime. So when will this term is non-zero?
At E prime.
Is like for which node V that this term will be non-zero.
U prime, V prime.
U prime and V prime.
Yeah.
Only when like E contains like only at the endpoint of E prime.
Yeah.
Then this term is not going to be non-zero. And so it's actually going to be exactly Xe prime. So we get to this one. Like at the endpoint of E prime, you get this term to be Xe prime. At another endpoint, you get this term Xe prime.
Yeah.
Then you might like Xe prime is opt. And this sum here, like this sum here is less than W over opt. Because of our because the value on E prime is small. So we get that okay, X now is actually shows that the oracle is feasible. Okay. All right. So back to the oracle again, like this looks like some problem that is easier than the LP, the original LP, because we kind of collapse all the constraints into one. That's first thing. And if the LP is feasible, if the LP have value at least up, it must be feasible. That's what we know. And also, okay, it's easier to solve, but if we can certify that it's actually not feasible, you can actually now construct a dual. That show that like you can construct the vertex cover showing that the original LP is not like has value less than up. Okay. So here is the algorithm. Our algorithm will basically like try to solve this easier oracle problem several times. Okay. So just start with weight 1 initially, and there are many days, kind of like before. Okay. And what we're gonna say is this: we're just gonna call the oracle on this weight. If it say infeasible, what do we know? We can construct the vertex cover, just like from how we constructed before, and this is gonna certify that we are done. Like this thing is gonna be a vertex cover of size at most opt. So we would be done. All right. Now, if it's feasible, then it will return some X. This X might be not at all matching. Because note that like this kind of solution where like some of the entry is much more than 1 is also a feasible solution for the oracle, all right? But it's gonna return some feasible point for the oracle. So call that X, call that thing XT. Okay. And now what I'm gonna do is I'm gonna define a gain vector to be like a times xt. Okay. And let's say that this gain vector is bounded above by rho. And now I just update the weights for each node. Like the weights here is like you have the weight for every constraint, for every node. You update the weight for each node. Okay.
But what is A here?
Oh, A is the matrix for the LP. This is A, which is the matrix that describes this LP. Right? This is, yeah. So I compute the gain vector and update the weights. And then I just repeat this. Whenever the oracle say infeasible, we are done. We get a vertex cover. And we're gonna repeat this for this many days. And at the end, I will take the average of all the x that I have computed so far. This is sum over all x, or like an average it. And my answer is gonna be like this average of x scale a bit down. Okay. So are we clear that what we need to like if whenever like we return y answer, this already gives you a vertex cover and we are done. So all we need to show is that if we return x, this is actually a fractional matching, a matching. Each of these xt might not be matching, but we're gonna say that like once we scale x down, like sum them up and scale it down, this is a matching. And also its size is big. Its size is close to all.
And so this is to solve the decision problem, and then we binary search over this.
Yeah.
Okay.
This is to solve the decision problem. I'm gonna claim that like this x is a fractional matching of size, basically at least our guess over like -4, like close to our guess. Yeah. Okay. And by the way, you see that this parameter rho is kind of is called the width of the oracle. It kind of dictates how fast this algorithm is. We will not like I will try to show later how to construct the oracle such that rho is small. But for now, let's talk about correctness for now. Okay. So for the correctness, all we need to do is to show that if we return x as an answer, then x is a fractional matching of this size. If this is the case, then we are done for the correctness. Okay. So why is that the case? Well, I will show this. I will talk about x bar, where x bar is just before I scale down x by this one. I will show two things. I'm gonna say that the size of x bar is at least opt. And x bar actually satisfies all the constraints up to this factor. Just these two things. If these two things are the same, this is the case, then we would be done. Why? Because once I scale it down, like if I scale, because if given these two things, don't look at the proof yet. Yeah. Given these two things, then we have that x and is just x bar scaled down by 1 plus 3 epsilon. Okay. Then from the first part, we would get that the size of x and is at least this thing, just scale things down. And also x answer would be feasible because it multiplied by like, yeah, because this thing is now scaled down. We scale this thing down. Okay. So, okay, let's try to prove these two things. What's the size? Why the size of x bar is at least up? Well, this is because from our oracle problem, we have that for every xt, the size of xt is at least opt. This is like what oracle guarantee. And x bar is the average of xt. So the size of x bar is at least opt too. How about this one? Okay. So this is where we use the guarantee of weight update crucially. Okay. So let's define the average gain of, like, this is h bar, which is just a sum of the gain over like the average gain of all the expert. So now expert kind of correspond to each constraint on each node. Okay. So we know before that, like this is like the average gain vector, right? And you can see that ax bar, which is just like this is the sum over all xt over t, and then multiply by t, divide by t. Yeah. This is just what the sum over t axt. Okay. And this is what is axt is ht. This is maybe yeah. So this is just 1 over t sum ht. This is h bar. Okay. So this is the gain vector on each day. This is ht here. Okay. So what do we know? We get that like ax bar is just h bar. But we also know that h bar is at most, like, we know from before that h bar for every expert I, or like right now is for every node, it's just at most 1 plus 3 epsilon. Why this is the case? This is because like, okay, this is because we actually know that what do we know? Like the oracle says this, that W ax, which is at most this one, which is this, right? But this is like h, like this is ht. So we get that W, maybe I write Wt at most 1. It means that like the guarantee of the oracle really just says that the expected gain on every day is at most 1. Just like in the beginning when we talk about weight update. So if the expected gain on every day is at most 1, we know that the average gain of every expert is going to be basically at most 1, 2. So every expert has the gain at basically 1, like 1 plus epsilon. So, and now because like we define like h bar is just the same as ax bar. So it means that ax bar is at most like 1 plus 3 epsilon on every constraint. Yeah.
Are we, when we set the gain vector, are we like setting it cleverly such that what you just said holds?
Yeah,
Okay.
I really like try to set the gain vector so that I have this guarantee.
Right, okay.
I want to make sure that our weight update has small gain every day. If that's the case, then the gain of the expert, every expert, must be small. If the gain of every expert is small, it means that our solution is close to feasible. So after scaling down, after scaling x bar down a bit, then we get xn, which is good. Are we good here? Yeah. I define the oracle such that, yeah, expected gain is small. Like the gain of the MWU is small on it every day. That implies that like our average solution is close to feasible. And the size is at least up. So once I scale it down by 1 plus 3 epsilon, we are done. Okay. Good. So to conclude, right, the algorithm here really just return a vertex cover of size up, of fractional matching, of size close to up. But you see that the running time and the running time of the oracle and the width of the oracle basically dictate the whole running time. Basically, if we can implement oracle with row, this algorithm will take something like row iteration. And on each iteration, it needs to call the oracle. So like we need to implement the oracle. And also like a time to update the weights, which is something like n, like number of nodes here. Right? So like we just update the weight here. This takes O(n) time. Okay. So the question is then, how do we construct the oracle? It looks like an easier question like than solving the LP itself. But let's try to construct the oracle. So, well, okay, let's recap, right? Now, our whole goal is to implement the oracle. That's what remains. And yeah, what we want to do, if we want to implement oracle with row, it means that we want to find, given any weight, W, we need to solve phi x such that this is true. And also this. You see, like because we define our like gain vector to be ax, and each we want that our gain vector on like the gain vector has size at most row. So this is just what it means here. To have width at most row. So it means what we want to solve is like we want to solve the average problem. This is the average problem, like where you just collapse all the constraint to 1. And also, if you look back at the original constraint, it doesn't it doesn't like violate the constraint by too much, by more than row factor. That's what it means. It doesn't need to satisfy if without row here. It means that x would satisfy the whole thing. But here it just means that x satisfy every constraint, but not quite. It's satisfied every constraint up to row factor. Okay, so you see this is the goal. All right. Now one way to implement the oracle with like 1 is just to solve the LP itself. Right?
Yeah.
So like that will give you x such that like it's at least up, or like all the constraint is satisfied, or say that it's infeasible. So that would say, okay, row is 1, but that's not useful because we want to solve the LP. Okay. So now you're gonna see like 2 other implementation of the oracle that is not like easier than solving the LP itself. Okay. So let me ask you some like just to get you like how to solve the oracle, how to get the oracle. Suppose that I ask you to just solve this problem, like just for exercise. Okay. Can you find x such that both of this is true? Well, yes. What you can do is like, okay, just set x1 to be 4. Then like here like it's at least 4, and x1 here would be like this thing would be at most 10. How do you see this? How do we see this actually? Like basically the idea is like what you should set is like to look at the guys here with smallest coefficient.
Yeah.
Right? It's like the guy with the best bang per buck. You want to make the sum of x to be as like quite big, but you don't want this thing to be like a big too fast. So just take the one with smallest coefficient and then like put value into that one. What about this one? Can we say that? Can we satisfy this one? It's going to be no, because okay, we know that like it's best to just put value to x1 because x1 has smallest coefficient, but we need to put value to x1 at least 6. But even the best bang per buck guy here, if you put this to be 6, it would violate 10.
Yeah.
So it's actually, you see like in general when you have just 2 constraints like this, where you want a sum of x to be at least something, and just another constraint, single constraint, it's super easy to solve. Just look at this constraint, look at the one with smallest coefficient, that's the guy with best bang per buck, and then just put the like just try to satisfy the first constraint by like putting all in to the best bang per buck guy. Yeah.
Are we looking at like, do we want to find the one with the smallest coefficient or the one with like the smallest coefficient ratios between the 2 equations? Because if it was like 10x1 and 20x2 for either, then I think the same logic would
So
apply.
normally if there are some coefficient here, then you would like look at the ratio of the coefficient, but here they are all 1.
Right, okay.
So we really just like you're totally right, but right now we are in a simpler situation. Yeah.
So are we gonna like say that the coefficient of like like an edge is like how many node, or the coefficient of like a vertex is like how many edges are next to it? Or for like I'm just trying to think of how to translate this to.
Right. So normally, like what will happen in our case is that the coefficient here will involve the weight. So it's not really like just the number of edges. And what will be the case is actually like it will be like the coefficient here will actually be the sum of the weight. Like if this is xe for he, The coefficient is like the sum of the weight on the two endpoint of HE. Okay. But basically, you see, in the Oracle problem, you basically have these two constraints. The first one is like just the sum of x is at least something. This one is just some constraint, one constraint. So the same algorithm works, right? The algorithm then is just to find an edge with the best bang per buck. That is the guy with smallest coefficient. Meaning that like you used to have this one, you find a like in notation it's like you find an edge with smallest here. This thing is smallest. Like when you that entry of E, this thing is smallest. But in our case of matching, they simplify a lot to just say that find an edge such that the sum of the two endpoints is smallest. So that's easy to find, right? Like you know the weight. The weight is given. Scan through all the edges. For each edge, you sum the two endpoints. Take the guy that has minimum weight. Take the edge that like the sum of two endpoints is minimum. That's your edge. Let's call that edge E prime. And then just say that, okay, you're gonna put all into E prime, like put the value of opt into E prime, so that, and everyone else is 0. If you do this, then the first coefficient, like first constraint is satisfied. Now, all you need to do is just say that, okay, once you satisfy this one, is this satisfied with the best bang per buck guy? If this is the case, that is this is satisfied, and return our x here. If not, then you know that it's infeasible. So you can just actually even get you can immediately get the vertex cover if it's infeasible. That's algorithm. So you see that this is significantly simpler than solving linear program.
Yeah.
And here's an analysis. Okay. So the running time is just linear. It's like kind of just scan through all edges, but it's linear. In general, like it's like computing this thing is just takes like number of non-zero in A. Okay. But what's the width? The width is not so good here. The width actually gonna be opt. Okay. Which is at most like n. So what do we need to show? We need to show that with our x that we return, it still kind of satisfy the constraint up to factor rho. And rho here is going to be as big as opt. Okay. So why is that? Well, like we want to show this thing. Like that is when you look at for every node here, the sum of the xe that we put here should be this sum is sum to at most rho. But okay, this is gonna be at most opt because basically we put like a single like we put like a for he prime we put value of opt here. So like yeah. So you see that like you agree that like the width is opt.
Yeah.
Okay, but opt is not 1. Opt can be as big as n. Okay. But what do we have here? It means that like we now get basically our width is opt. So the number of iteration is this one, and on each iteration, we call the oracle once. That takes this much time, or m time, and update the weight in O n time. So this is like running time. There are this many iterations that we call the oracle. On each round, we spend linear time.
You said opt is at most n?
Yeah. Why opt is at most n?
Well, for the runtime for iterations, should you kill the opt and the O notation? Does the opt need to be n or no?
Opt is at most n. So this is at most m. This is at most m.
Yes.
This is at most n. So you get mn.
Oh, I see. Okay, thank you. Sorry.
Yeah. Okay. So yeah, we're gonna finish here. Let me finish at least here. So you can see that for meshing, we actually can improve the Oracle running time from just from computing trying to scan through all edges with smallest weight in linear in OM time. Instead of spending number of edges time, we can improve it to ON. And the reason is this. Our goal is just to find the edge with smallest weight, the sum of its endpoint is smallest. But you know that the weight, only weight of vertices incident to E prime will be updated. On each round, we have edge E prime, and we update the weight of E prime here. So only edges. So now, we update the weight of the endpoint of E prime here. So what happened is that the edges incident to these two guys will have its weight updated. There are only two n of them that is updated. So basically there are 2n such edge that you need to update. So the time to update the Oracle running time is, instead of scanning through the whole graph, just need to look through, just need ON time to update it. So actually the running time is from here m, you can improve it to n. So running time is then n squared. So next time we're gonna see how to improve it further. And this is called there is this technique called width reduction. We're gonna get algorithms such that the running time is linear, but the width instead of n is 4. So much better. So width reduction is really kind of important technique when you look into weight update, and we'll see how to do it next time. Right, okay, yeah, see you next time.